So we would like to obtain the extrema of this function if available. We are going to use MATLAB, and what we are doing is that instead of writing in the command window, we are using LiveScript here. So click on New LiveScript, and you have a LiveScript here to type in, okay? So the first thing is to define symbolic variables x and y, and then we shall go ahead and type in the expression for the function x to the power 4 plus 2 times y to the power 4 minus 12 times x times y square minus 20y square. Okay, so we typed in, and let's look at a graph of the function to get an idea of the relative extrema. And what we will do is just to make the graph smoother, we will go ahead and use this feature called mesh density. 60 works good for me. I'll see what works better this time. So I went ahead and asked it for that. Okay, and just a second. Okay, so let's go ahead and bring the graph here. Okay, so we can see that if we look at the graph, looks like we have a saddle point here, and it may need some more window to be graphed in. So let's go ahead and increase the window, or just give it a different window. Okay, so we may do this, add in just here, say -6, -6, okay, and then keep everything else the same. Okay, let's see what kind of graph do we get now. What did I mess up? Yes, I didn't type a 6 here. Okay, hopefully it shall be fine this time. Okay, all right, so it is. Okay, so what we notice here is this, that looks like that we shall have uh, two minimum points of two minimum, and this looks like a saddle point. So let's go ahead and examine the partial derivatives. Okay, so we will take fx equals the derivative of f with respect to x, then fy equals the derivative of f with respect to y. And I again forgot reminding you that after we do everything, we just use control enter. Okay, so here we can see that if we look at the two partial derivatives and we set them equal to 0, then there is one obvious solution, and that is what? 0, 0. So if we did this, so here is 0, 0, and that appears to be a saddle point. And then we have to go to the others and then look at it a little more globally. Okay, so we go ahead, and now I am going to define fxx as the second derivative of f with respect to x, fyy as the second derivative of f with respect to y, and fxy as the mixed partial. Okay, so derivative of f partial of x with respect to y, right? And let me again just do control enter. And here we have the partial derivatives and the second partials. Now let's just for the sake of the look of the graph, let's just go ahead and change the length of the z window. Okay, and when we looked at the graph, Just a second. 6, I think, yeah, negative 500 to 500 should be good enough. So I did Control Enter, and then graph should come up. Okay, and here it is. And I am just going to bring the graph in from the figure window. So here we have a graph, at 0, 0, we have a saddle point, and there are two minimal. So let's go ahead and look at a contour plot just to get an approximate position of these two a little more precisely. So for the contour plot, we shall ask for f contour, and we want that for f, and our range of x, y values are negative 6, 6. Okay, and then we want, remember, this is a good idea to keep the line width wide. So, and 1 is wide enough here. And then the second thing is we want, I like it to be black, the line color. Okay, so and again, as I said before, hexadecimal is the only way I know right now to be able to enter it. And then, very important, we will write the level list. And what is the level list? That we are just giving the values, okay, that the function fxy takes between negative 500 to 500. So I'm going in intervals of 10, like negative 500, negative 490, and upwards. And if I do Control Enter, I should get a graph, okay, of the contour line. All right. And here is a graph of the contour line. And you can see here it became like, I would say, unnecessarily dense. Let's just bring it from the figure window. Okay. So here at 0, 0, we have the saddle points, and these two eyes are indicating the points of minima as we saw. Okay, so let's see. So for instance, the x, y coordinates of this point are 3.6 and negative 3.9. So what we will do is use the fsolve feature of MATLAB, okay, for solving this set of two equations, the nonlinear equations in x and y, by a numerical solver, okay, where we will use this as the starting point that we got from the contour plot. So again, recall that we have obtained these equations by setting the first partial derivative with respect to x and y of f equal to 0. So what we would do first is that first we are going to define an anonymous function, okay, using these two variables. Okay, so just a moment. Okay, so in the first slot of first coordinate, I'm writing 4x cubed minus 12x squared, and then separating them by comma. In the next one, I'm writing 8y cubed minus 24x times y minus 40 times y. Okay, so this is our anonymous function defined. Now for fsolve, we are going to define a second anonymous function. Okay, and what we will do, that is, we will just want to combine x and y into a single two-dimensional function argument. So the way we do that is that we just created another variable u, and then we already have our z defined. Okay, so u1, u2 for the two components. Okay, and then so we got these, and then we will have a comma. Okay, and then we have the coordinates of the starting point that are 3.6, 3.9. Okay, so let me check if everything came out to be all right. Okay, here I have to put parentheses, I forgot. And that's what was creating all those wavy lines. So let's make sure that I didn't mess up anything else. Here I did. I typed x square for y square. So now let me press Control Enter. And so we have a solution, 3.6247 and 3.9842. So if we go to our, so we just got coordinates of this critical point here as 3.6247 approximately, and the y coordinate is 3.9842. So by symmetry, this one will have the same x coordinate, and y coordinate will change to its negative. So what we get now is that these are the approximate coordinates of the critical points as approximate solutions of this equation. So if we evaluate f at this, we are going to get, how much will be the value? That will be negative 331.35. And of course, we saw in the figure that they were just symmetric. So if we add a negative here, still it will be approximately the same. Yeah, it is actually the same. All right. So we got a saddle point and two absolute minimum here.